Hello everyone and welcome to this, my video on translation of functions. A brand new section of work, yes, because this is massively important. If you are doing methods 1 and 2 at this moment in time and you are going, I'm not even in Australia, it doesn't matter. If you are doing any algebra-based course, translations and reflections and dilations of functions is massively important. In fact, so much of the methods 1 and 2 course is devoted to this. It is really important. So we're going to sort of ease into this now. And as you can see behind me, and I always put it behind me, there is our learning objections. Know what it means to translate a function. Know what it means by the term Cartesian plane. Understand the notation of translation of functions and apply translations to sketch graphs. Now, obviously, the most important thing here is the idea of sketching graphs. We're not plotting every single point. We are taking the key points of any graph and then effectively sketching them. And by that, I would mean you're drawing sort of a quick set of axes. You're putting a y there, you're putting an x there, and then you're drawing some sort of function. Let's see if I can draw a y equals x squared. Y equals x squared. We'd have some arrows on the end because our domain probably isn't limited. And there we go. Is that the end? No, sadly not, because you'd probably be expected to put some important coordinates on. So this is what makes a sketch a sketch. This is what's telling the examiner you actually know what it is you are doing. So if I was marking this, I'd be really happy with that as a sketch. Well, sort of. I didn't quite go through the origin, and I'd probably try a bit better. But I'm using electricity. That's this Apple Pencil thing, trying to draw these graphs. But generally speaking, what we're looking for is important coordinates. Now, yes, you've got to put x and y axis crossing points. That's really important. You've got to give an indication of whether this thing is going to infinity and beyond, or have we limited our domain? What is the function? These are all sketches. But what happens when I move this thing left or right, or in fact up or down? Then what we're saying is we are translating our function. Now, obviously, I like to recap stuff as part of the start of all my videos, but there is so much before to recap that let's just say it's building on what we've done before. But fundamentally, if you know the basic shapes out there that are sort of what I call base functions, y equals x squared, y equals x cubed, y equals the root of x. If you know that x squared plus y squared equals r squared is a circle. If you know that y equals plus or minus the square root of r squared minus x squared is also a circle. But if I get rid of that plus and minus and make it either a plus or a minus, then I get a semicircle. That's really important. What else have you got to know? Y equals 1 on x. And probably y equals 1 on x squared. They seem to be the main functions that we tend to deal with. If you know fundamentally what they look like, then you can move them up, down, left, right, flip them, grow them. It doesn't actually matter. But methods is all about visualizing those graphs. Know what they look like, draw a quick sketch. Right, so what is Cartesian plane? Let's go back to year 6 maths. But before we do that, can you do me a massive favor? Can you please subscribe to my YouTube channel? It is massive when people do that. I generally get about 3 people a day do it. What it does is it just shows me that people are out there, and you, in fact, are watching these videos. That really does make it all worthwhile, rather than me sitting in here going slightly mad. And if you head over to mathsguru.com, all the lesson notes, everything I'm doing at the moment is downloadable. There is online VCAR questions. There is so much over there for you to be able to do. Enough of that? I think so too. What is a Cartesian plane? It's a fancy name for a set of axes. Basically, I've just said it there. To quote the Cambridge textbook, and I am so grateful to Cambridge for allowing me to use their worked examples. Guys, you rock. It's a great textbook. The Cartesian plane is represented by the set r squared. Now again, notice there that double r as we call it. That's double r. Yes. Of all ordered pairs of real numbers. What on earth is an ordered pair? Well, we've done that in the previous part of the course. It's just a coordinate. Is it clearer now? Maybe not. Now, transformations in this section of the course associate each ordered pair of r squared with a unique ordered pair, i.e. we're going to do something to our coordinate and it's going to turn into something else. It's going to move or grow or shift. Now, notation is really important in methods, and hopefully you've got that. Every point on a graph has a coordinate expressed in that form. Yes, every single coordinate is expressed x, y. X value and a y value. Now, if we were to move it up, down, left or right, then what we're going to be doing is we're going to be translating that coordinate. So for example, if I have the coordinate 1, 2, and I decide to move it 2 places that way, which of those coordinates is going to change? Is it going to be the x coordinate? Is it going to be the y coordinate? All right, well, hopefully it's going to be x coordinate. And what's going to happen to the x coordinate? Well, again, pretty basic maths. That 1, I'm going to add 2 onto it. And so it is going to translate to 3, 2. Notice it's not going up or down. In this instance, I was moving it simply 2 to the right. Now, that's great, because now I've got a sort of a visual way, a quick check way of saying, well, if I know what an initial coordinate is, then all I'm going to do is basically add on or subtract to either the x value or the y value. All right. Now, as I say here, if we are going to move things up or down, we will be changing our y coordinate. If we move things left or right, we're going to change the x coordinate. So the question is, what on earth does that notation there mean? What is this x plus 3, y? Well, for those of you who are pausing the video, it would mean that every x coordinate has had 3 added to it. Now here, I took one individual coordinate. What I'm now saying algebraically is, well, let's take every x coordinate and add 3. Well, wait, what's that going to do to my graph? If I'm taking every coordinate, let's say a parabola, and I'm adding 3, then hopefully you realize it's actually going to move 3 places to the right. Yay! And actually, when we see things in this format, it's lovely because we go, oh, well, it's moved 3 places to the right. It's rotated. It's reflected in the y-axis, and it's, you know, dilated by a factor of 2 from blah, 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 blah. But I'm rushing ahead. So again, there are lots of different ways of doing this. So again, I suppose because this is the fundamentals, what does that mean? X, y minus 2. Which way is it moving it? Well, it's taking all my y coordinates and it's moving all of them down by 2. It's subtracting 2. It's moving the whole graph down by 2. So not moving it to the left or right. It's just moving it up or down. We can even change both. That would sort of make sense, wouldn't it? So looking at translations only, what does that tell you? Well, we're moving all of my x values 1 to the left. We're moving all of my y values 4 up. So now we start looking at things like, well, at the moment, when I'm looking on my computer screen, I'm not actually seeing me, I'm seeing my image, all right? I'm seeing a copy of me, but in this situation, it's actually flipped, all right? Now we have a notation for that, and that notation is x dashed, y dashed. What we're saying is, if I have a coordinate x, y, and I do something to it, that is going to become x dashed, y dashed. Why is that important? Well, as it turns out, we can look at something pretty funky using some pretty basic algebra. Now, you're going to turn around and go in a minute, oh, yeah. And a lot of teachers out there just turn around and go, oh, no, love, just use shortcuts. It's so easy to use shortcuts. And I will come back to the shortcuts in a moment. But there is a huge value to showing how the algebra works. So we're looking at an example. What have we got here? We've got the graph of y equals x squared. Nice and easy, drawn on Desmos. We love, love, love Desmos. No, I'm not sponsored by them, but it's just visual. Have we got the important points marked? Not at this moment in time. But had I sketched it, I would have put some dots there. I would have put 1, 1. I would have put 0, 0, and I would have put -1, -1. Now, a lot of people turn around and say, well, can't I just put 0 here? The graph's already got a 0 on it. And my argument is no. Methods expects you to be able to put coordinates, full coordinates, with the brackets, with the comma, put it on. Yes, it's tedious, isn't it? I mean, oh, this course is horrible. But that's what they're giving the marks for, all right? And you've got to show the examiner, because at the moment we've got this beautiful scale shown, but you've got to show the examiner on things that doesn't have scales where those coordinate points are, all right? So as I've said here, we can sketch it easily. What would be the equation if I was to take this original function and move the whole thing 2 units to the right and 4 units up? Okay. Well, as I said a moment ago, we can say that each coordinate is given by x, y. Right? Every single coordinate on that is described by x, y, and we know that that's going to move to sort of some x dash, y dash. Well, this is my original. And what have I done to it? Well, I'm moving 2 to the right and 4 up. So that means I'm going to have x plus 2, y plus 4. So these are my original. Right, so again, this is my original set of coordinates. This is what I'm becoming afterwards. But we're now saying that these are actually my image. So what I do is, excuse me, I changed pen color. I now let that be x dashed, and I let that be y dashed. And you're going to say, well, why am I doing this? Well, I've got an equation at the moment that's got y equals x squared. What I need to do is replace that y and x with an x dashed and a y dashed, because I want to know where the coordinates are moving to. So looking at this and simply equating it, I can now say, well, therefore, x dashed is equal to x plus 2. To get to my new x coordinate, I take my original x coordinate and add 2. And by the same logic, I say y dashed is y plus 4. Now, because I want to get rid of this x and y and replace it with x dashed, y dashed, I now have a beautiful way of doing that, because I can just rearrange this. So I now know that x is the same, sorry about that, as x dashed minus 2. And y is equal to y dashed minus 4. Happy with that so far? Just some basic algebra. All I've done is basically say, well, look, I'm starting with x, y. I'm adding 2 to my x values. I'm adding 4 to my x values. And I know that they are now labeled as my image. And I can now write 2 equations, rearrange it a little bit in terms of x and y, because now my original equation was, as I say here, y equals x squared. What I'm going to do now is I'm going to replace that y with y dashed minus 4. Because I've said here, anywhere I see a y now, I can replace it with y dashed minus 4. That becomes equal to x. Anywhere I see an x, x dashed minus 2, and then all squared. Do a little bit of manipulation, because obviously we never like to have anything starting with y dash minus 4 or whatever else. We're looking for it to be y dashed on its own. So I'm going to manipulate that to become y dashed is equal to x minus 2 squared plus 4. Sorry, maybe I do a dash there. And because that's the equation of my image, I don't need the dashes anymore, all right? Because now what I know is my translated function could be written as y equals x minus 2 squared and plus 4. Now, for those of you who are ahead of the game, that's interesting, isn't it? Because when we were moving 2 to the right, we noticed that became negative 2 inside. And a lot of teachers turn around and go, oh no, it's just the rule. It's just the rule. When you go left and right, it's just the opposite of what you're expecting. I don't know why I keep doing that accent. It's a bit weird, really. But hopefully that explains why. And I always say, once you've sort of worked this out, anything inside that bracket is the opposite of what you're expecting. That minus 2 leads you to believe it's going to go 2 to the left. It's not. It's going to go 2 to the right. And that plus 4, because it's outside, works in the right direction. But if you were never unsure, if you weren't ever sure, you can basically write your translations, transformations in that format, equate it to x dashed and y dashed, a little bit of algebra, and lo and behold, out drops your answer. And of course, you can always pause these videos and go back. There is so much stuff you can sort of go back and pick up the second time. And there we go. So the translated function or image would have that equation here. And if I was to draw that, then what we would find out is that we would have our minimum point here, our 0, 0, would move 2 places to there and 4 up. All right. So I would now be able to put a cross there and then be able to turn around and say, well, where would my 1, 1 move? Well, my 1, 1 was, where's my 1, 1? Here. It's going to move 2 across and it's going to move 4 up. 1, 2, 3, 4. It's going to end up there. So obviously, hopefully, if I've got this right, it's going to be there, and that one's going to be there. And then I can pretty much sketch my new graph. Now, again, the great thing about this, and this is all part of completing the square form, and this is where method starts to mesh and hopefully build up and interrelate. What we can now see is that this value here, that negative 2 and 4, or at least the 2 and the 4, are now the coordinates of my minimum point. We also know that because of this doing what it's doing, excuse me a moment, I don't know what's going on there, because of this, we have an axis of symmetry straight down the middle. We know that quadratics have an axis of symmetry, and it just so happens it has an axis of symmetry at x equals 2. Well, looking at the completed square form, what do we notice? That 2 tells us where the axis of symmetry is. And when we know the axis of symmetry, we can find y values and turning points and all that type of stuff as well. So there's a lot here, yes? So that's the algebra way of doing it. But guess what? Yes, there are shortcuts. And not everybody likes this. So I've tried to sort of put this in a way that makes sense to everybody. What we're saying is, if we have a positive x translation by h units, and methods loves using letters, what we're saying is, if we move that way h units, then what we do is every instance of x in our equation, we replace with x minus h. Now again, this takes practice. If I'm moving that way, a negative translation by h units, then I replace it with x plus h. And these are the type of things you put in your summary books or you just memorize. If there is a positive translation in the y-axis or positive y translation, then you replace the y with y minus k. Again, notice positive, negative, positive, negative, negative, positive. So again, counterintuitive and all those type of things. But let's go back and see what that means with doing it the shortcut way. Well, if I had y is equal to x squared, and I'm going, what was it, 2 units to the right and 4 units up, then what the rule says, when I move to the right, I'm replacing x with x minus, and in this situation, 2. So I'm going to get y is equal to x is going to become x minus 2 all squared. Now, obviously, that's one step. We've got to work through a process of translations, because that's this one done. That's the 2 done. Now I'm going to do the vertical by 4, and it says to replace y by y minus k. So 4 is my k, y minus k. So now I'm going to replace y with y minus 4 is equal to x minus 2 all squared. Do a little bit of funky magic. And what do we get? The same answer as we've got before. So in that situation there, same outcome, same outcome. And later on, it gets a little bit more complicated where we start to combine translations. Now, have you subscribed to my YouTube channel? I know it's a bit weird. I keep asking this, but if you have, it means the world to me. Who watches maths videos? Nobody. Everyone's out there watching TikTok or whatever else. So if you can subscribe and tell your mates, because hopefully these videos make awesome sense to you. If you can tell your mates about it, I would be so, so grateful. Yeah, my YouTube channel has taken years to grow, and I'm almost at 10,000 subscribers. If you could do that, honestly, as I say, it would be massive. Right, what have I got next? Oh, some examples. We like examples. And again, thanks, Cambridge, for letting me use your examples. Find the equation of the image of the curve with equation y equals f of x, where f of x is equal to that. So again, the thing about methods is we don't have to use a lot of random language. Y equals f of x. We've told you f of x equals 1 on x. So why don't we just say that y is equal to 1 on x? Go figure. Why? Because methods is all about tricking you, believe it or not. Y equals 1 on x under a translation of 3 units in the positive direction of x and 2 units in the negative direction of y. Now, again, we can do it the algebra way and we can do it the shortcut way. So I'm going to show you the shortcut way first. Again, if you're not sure why, go back to this, put it in your summary book or download the notes from mathsguru.com and job is done. So what do? We remember that in this situation, we've got to place x with x minus 3. So that's going to become y is equal to 1 on x minus 3. That's the first stage. And then we're going to replace y with y plus 2. Remember, we're going down. That's minus 2. So y by y plus 2. So there we go. Y plus 2 is equal to 1 on x minus 3. Then y becomes equal to 1 on x minus 3 minus 2. There is my answer. The world goes crazy. Now, what I'm going to do is let's move that over. So we've got a bit of room for the algebraic method. Let's move that up there as working out. And let's try now the algebraic method. Right. What do? Well, we know that our original coordinate was x comma y. That means if we do all of this together, what do we say? That's going to become x in this situation plus 3 and y minus 2. Remember, I'm not using the shortcuts. So in this situation, we'd be adding 3 to each of the x values and taking 2 away from the y values. What do we do now? Well, we go, let that be x dashed, let that be y dashed. So therefore, we've got x dashed is equal to x plus 3. We've got y dashed is equal to y minus 2. Well, we've got my original equation in terms of x and y. We want to swap those out. So I've got to rearrange this to get x equals, rearrange that to get y equals. And so what do we get? We get x is equal to x dashed minus 3. We get y is equal to y dashed plus 2. And what do we end up doing there? Well, we now take my y equals 1 on x. Everywhere I see an x now, I'm going to do x dash minus 3. Everywhere I see a y, I do that. So that's going to become y dashed plus 2 is 1 on x dash minus 3. We do a little bit of tidying up, and I get 1 on x dashed minus 3 minus 2. And as I've said before, we probably don't need the dashes. He says deleting half the answers because we know that's now the equation of my image. And do they match? They do. Which one do you like? Totally up to you. Okay. Sometimes the algebra way is quicker, particularly for complicated ones. Other times the substitution way is quicker as well. We've got another example. Knowing the theory means we can now sketch some pretty complex graphs. Because I now know, and this is massive in methods, you've got to start looking at this and saying, well, okay, first things first, what is the base graph? And secondly, what have I sort of replaced to get to here? So in this situation, hopefully you're all aware that the base graph there would have to have started as 1 on x. What does a graph of 1 on x look like? It is a hyperbola. And again, beautiful hyperbola. Where are the important points on there? Well, we've got some asymptotes. Yeah, at y equals 0. We've got an asymptote here at x equals 0. It crosses through that point there, which is 1, 1. It crosses through that point there, which is minus 1, minus 1. They are my important pieces of information. That's a quick side sketch. Now, you'll notice that nothing here says start with a base sketch. No, of course not. But by starting with that, I've got a good chance of knowing what to do next. So what do we seem to have done? Well, we seem to have replaced x with x minus 2. Well, if I'm using the shortcut, that means that I've got to think in reverse, because that x minus 2 means I've moved it 2 places to the right. Have I done any up or down? Nope. Why not? Because there's no number on the end here, right? So anything that's changing the x basically is a horizontal. Anything over here is a vertical. And I've got everything I need to know now, because all I've got to do now is take my graph, this one here, and move the whole thing to that way. So if I was to, again, try and draw axes, where was my asymptote originally? My asymptote originally was x, I don't know why I wrote x equals 2 there, by the way. That should be x equals 0. X equals 0. All right, we knew my asymptote was x equals 0. Well, that's been moved 2 places to the right. So what I'm now going to do is draw my asymptote at x equals 2. I was ahead of myself. Has the graph moved up and down? Nah. So I can now go and I can draw a beautiful hyperbola here, because let's delete that again and try that one again. All right. Probably a bit closer, but I'm struggling with space on here. Now, have I finished? No, because ideally what I need to do is put on the fact that I know where this coordinate has moved. That coordinate was 1, 1. It's moved 2 places that way, so the x value has changed, so that now is 3, 1. This coordinate was minus 1, 1. It's moved 2 places to the right, and so that's now going to be 1, minus 1. So there we go. So that point there is 1, minus 1. And am I done? Nope, got to put some arrows on there because my domain wasn't restricted. Anything else I've got to do? Probably put the equation on. But whenever we do a graph, we always have to put on my y-axis. And in fact, x-axis intercepts. How do I find a y-axis intercept? Oh, I put x equals 0. All right, so if I now take this here and put x equals 0, what do I get? Y is equal to 0 minus 2 minus a half. So I now know that coordinate there is now 0, minus a half. And believe it or not, there is a beautiful sketch, which I am hoping, if I put a y there and an x there, any methods examiner would be doing cartwheels for, because it's beautiful and colourful, probably not so much. What about the following functions? What on earth here? Well, let's look at the base functions. What has happened to this one here? Well, I would say that that had a base function of y equals x squared. And I would say that has a base function of y equals the root of x. Well, again, knowing what the base function of y equals x squared is, I would draw a quick margin sketch. And again, this is really bad because that should go through the origin. And I should draw a quick sketch here of a square root graph. Right, okay, so these are my base graphs. That's not my final answer. What am I going to do here? Well, I've replaced x with x minus 2. That means using the shortcut. I've basically got to go, whoa, using the shortcut, what can I do? That's 2 places to the right again. So now I would be taking this, and I would be shifting it 2 places to the right. Yeah, making sure that that is now 2, 0, putting that coordinate point in on that coordinate point, my arrows and what have you. And there we go. I've got a pretty decent sketch. What about the next one? What's this x plus 3? Well, it's counterintuitive, yes, and that's what I start to build up. It's not moving 3 places to the right. It's going to move 3 places to the left. And so I now know that that point was 0, 0. That is now going to move to minus 3, 0. And I'm effectively going to draw something like this. Oh my goodness! I now have an x-axis, sorry, a y-axis intercept. I would have to find that there. And x equals 0. That would therefore be 0, comma, root 3. Now again, a lot of people turn around and go, oh, do I have to write that in decimals? No, you don't write it in decimals because methods, unless otherwise stated, should always be written as an exact value. And yes, you're going to have to get used to using surds. Have you subscribed to my YouTube channel yet? It feels like this is very needy now on my part, but if you could, that will be great. Now, obviously, again, we've got this base function, we've got a sketch transform functions, but we're going to try and trick you with notation. Why do we try and trick you with notation? Because that's all methods is. When you see past the smoke and mirrors, life is so much easier. So here we go. Oh, he says trying to highlight. We didn't do the highlighting. There we go. What is that? What on earth does that mean? What it means, take your original function and everywhere, because normally a graph or a function is written as f of x. If I have y equals f of x plus 3 and you compare them, what's changed? They've replaced an x here with an x plus 3. And there we go. So what it's telling you is everywhere you see an x in the original function, replace it with x plus 3. So my original function is 1 on x. And so in which case, y equals f of x plus 3 would be equal to 1 on x plus 3. And again, how would we sketch that? We would sketch the graph of a hyperbola, yes, and we'll move it which way? 3 to the left or 3 to the right? I don't quite know which way I'm pointing because it's all backwards. Yeah, but in that plus 3 means I'm actually going to move it 3 left. So very quick sketch. Draw my asymptote here at x equals negative 3. I know that a hyperbola would now look like this. What? Oh, don't let it touch that asymptote, by the way. You get told off. With this value here, I can probably find. Why? Because I'm going to let x equal 0. And so that one there is going to be 0, comma, 1/3. Ka-ching, outside of the arrows and everything else. That's a pretty decent sketch. What about this? Huh? F of x minus 3. Oh, it means just take the f of x and minus 3. Well, in which case, the y equals f of x minus 3. Well, f of x is 1 on x minus 3. What does that tell you to do? Well, take the base graph of 1 on x. There's no horizontal translation. It's just going to move the whole thing down by 3. So in this situation, I'm going to have a horizontal asymptote at y equals negative 3. Okay? And again, notice how I draw the asymptote first. Why? Because that then lets me draw the rest of the graph. I know how it looks. I've got an asymptote here at x equals 0. So that's going to go like that. And this is going to look something like that. I can find that. Yes, how on earth am I going to find that? Well, we're not going to put x equal to 0 in that situation because it's on the x-axis. We'd put y equals 0. So we're going to have 0 is equal to 1 on x minus 3. 3 is 1 on x. X is 1 on 3. If that's too quick for you, sorry guys, slow it down and have a look. But I now know that that point there is 1 on 3, comma, 0. So just some basics of knowing how the graphs look makes life a lot easier. Another example, I know this video is long, but I have to say this stuff is so critically important, it is untrue. For y equals f of x equals x squared, sketch the graph of the following, labeling asymptotes and y-axis intercepts. Y plus 2 is equal to the f of x plus 1. Well, again, everywhere I'm seeing an f of x, if I know f of x is x squared, then f of x plus 1 is simply going to be x plus 1 all squared. So change pen color. So now y plus 2 is equal to x plus 1 squared. They're trying to trick us. Let's rearrange it. X plus 1 squared minus 2. And again, looking at this now, what does that plus 1 mean? That's 1 to the left. What does the minus 2 mean? 2 down. Yay! So again, I can now draw this. It's a parabola. If it's a parabola, I now know that this here is my turning point. So my turning point is going to be minus 1, minus 2. So I'm going to do minus 1, minus 2. There is my turning point. I'm going to draw a sketch. That's going to make sure that that is my minimum, and I'm going to go up here. Now again, the problem with this is, what if that goes to the origin? I've probably stuffed this up. So what I probably want to do is try and work out what my x-axis intercept is going to be first, before I draw any other points. Because I can do that by looking at this. What's my y-axis intercept? 0 plus 1 is 1, squared is 1, minus 2 is minus 1. So as it turns out, that actually does go through here. So that's going to be, oops, yep. Try that one again. 0 minus 1. Can I find this point here? Yes, I would let y equals 0. So let's just do that, because again, a lot of people get very scared about surds and they go, oh, it's too hard. This is methods. I'm so sorry. You've got to get used to this. So 0 is equal to x plus 1 squared minus 2. Add 2 to both sides is going to be 2 is equal to x plus 1 squared. Square root both sides is going to give me root 2, which is plus or minus, is equal to x plus 1. And so x is going to be equal to negative 1 plus or minus root 2. Now, what does that mean? It tells me that I've got 2 x-axis intercepts. Does that make sense? Well, hopefully it does, because I've got one here and one of them here. And the chances are this one here is going to be minus 1 plus root 2, because that's going to be the bigger value. And this one here is going to be minus 1 minus root 2. And don't forget the comma zeros, he says, forgetting the comma zeros. We got some arrows, we have the x and the y, we put the equation on. Oh, don't forget to label this minus 1, minus 2. And again, that is a sketch of a graph. Did it take me long to do? You're going to turn and say, yes, forever, because you haven't shut up yet. All right, easy. Be nice. Yes, it took me ever because I'm trying to explain it. You were doing that in an exam, you'd smash through it relatively quickly. All right, now I'm just going to review the learning objectives. Is that important? 100%. Did I cover? Do I now know what it means to translate a function? Oh, yes. Left and right and up and down. Do I know what it means by the term Cartesian plane? Yeah, set of axes. Understand the notation of translation of functions? Yes, because we've got x dashed and y dashed, and we know that we can do all sorts of stuff. And can I apply these to the sketch graphs? I should Coco. Well, guess what, guys? That is the end of this particular video. Thank you so much for watching. Hopefully it has been useful. Please subscribe to my YouTube channel if you can. Tell your mates. Okay, the only way I seem to be able to grow is through word of mouth. I'm over there on TikTok and Instagram and all that type of stuff, so maybe I'll see you there. But for now, goodbye. I will see you in another video. Take care, guys.